Hi, I wanted to make a video to talk a little bit more about one of the points that I was making at the beginning of class this week. I was talking about using a sample mean to estimate a population mean. In this example right here, let's say that we're interested in what the mean IQ of the US college student population equals. What that means is that we're interested in what number we would get if we actually recorded the IQs of all of these people right here and then added them all up and then divided the total by this number that you see right here. In other words, we're just interested in what the unknown population mean equals. So we don't have time to record the IQs of all population members because you see it's a pretty large number. So we can't actually calculate the population mean. In order to calculate the population mean, we would have to actually have all of these IQs recorded so that we could actually average them. But we don't have time to record all of those IQs from all population members because it would take too long, or it would be too expensive, or it wouldn't be possible. So instead, we're going to randomly select a sample of participants. We're going to randomly select a sample of college students living in the US and record the IQ scores of all members of our sample and then calculate the average of our sample. We're going to calculate the average IQ of our sample by adding the IQs of all members of the sample, dividing the total by the number of people in the sample. And we're going to use the mean of our sample to estimate the population mean. We're going to calculate the sample mean to estimate or to get a rough idea of what the unknown population mean equals. And we're going to hope that the mean of our sample is somewhere close to the mean of the entire population. We won't actually know for sure if the mean of our sample is close to the population mean because we don't know what the population mean equals. But we're going to just hope that we did a good job of estimating the unknown population mean, and we're going to hope that our sample mean is somewhere close to the mean of the entire population. So this asks, what would happen if we used a smaller sample, and what would happen if we used a larger sample? So what effect would the sample size have? Well, first let's look at what would happen with a smaller sample size. Since it's a random sample, meaning we randomly selected our participants, you can see that right here, that means that we're going to be more likely to get a sample with a sample mean close to the population mean, and we're going to be less likely to get a sample with a sample mean further away from the population mean. So let's just say that this green area, we're more likely, once we record the data values of all members of our sample and calculate the average of our sample, we're more likely to get a sample mean in this green area, and we're less likely to get a sample mean in this black area out here, or this black area out here. So more accuracy is more likely than less accuracy. That's just because we're doing a random sample. And you notice I didn't use any numbers under here and on my number line, and I also didn't use a specific sample size. The reason is because those numbers don't actually matter for this example. I'm just trying to make a couple of general points about why the sample size matters. Now let's look at what would happen with a larger sample size. We're still using a random sample, which means that we're more likely to get a sample mean somewhere close to the population mean, somewhere in this green area, and we're less likely to get a sample mean further away from the population mean, meaning somewhere in this black area down here or somewhere in this black area up here. So we just talked about what's happening because we're using a random sample. We're saying how since we're using a random sample, we're likely to get a sample with a mean somewhere in the green area, and we might underestimate a little bit. We could easily underestimate the population mean a little bit. We might get a sample mean down here, or we might easily overestimate the population mean a little bit and get a sample mean up here. But we're typically going to get a sample mean somewhere in the green area, and only every once in a while, or only occasionally, we'll get an extreme sample mean that's quite a bit higher than the population mean. And every once in a while, we'll get a sample mean that's quite a bit lower than the population mean in this unlikely area down here. And then the same thing for the larger random sample. You might, or we will actually often underestimate a little bit in this area, and we'll often we'll often overestimate up here, but we'll only occasionally get a sample outside of this area. We'll only every once in a while will we get a sample mean up here or a sample mean down here, because these are in the unlikely areas. Now, what effect does the sample size have, or why does the sample size matter? Well, notice that when we use a larger sample and we calculate the mean of a larger random sample, this green area shrinks. It's not as wide as it is over here with the smaller sample size. So when you use a larger sample size, you're more likely to have, well, how should I say this? When you use a larger sample size, you're likely to have a sample mean that's even closer to the population mean compared to if you used a small sample size. So using a smaller sample, whenever you use a random sample and you use random sampling, you're more likely to get a sample in the area closer to the population mean, and you're less likely to get a sample in the areas further away. That's true for both sample sizes, but you can see that random sampling works even better when you use a larger sample size. So let's try to summarize. When you use random sampling, you are more likely to get a sample mean closer to the population mean in the green area, and you are less likely to get a sample mean further away from the population mean in one of the black areas. When you use a larger sample size, you are likely to get a sample mean closer to the population mean than if you used a smaller sample size. Or I could rephrase this and say, when you select a larger random sample, you're likely to get a sample mean closer to the population mean than if you than if you selected a smaller random sample. So when you select a larger random sample, you are likely to get a sample mean closer to the population mean than if you had selected a smaller random sample. So just trying to phrase this right. Then you just being a little bit picky. I think this sounds good right here. When you select a larger random sample, you are likely to get a sample mean closer to the population mean than when you select a smaller random sample. That's just because the green area shrinks and you have even better accuracy. So let's look at this sample. Let's look at this outcome right here that's one tick mark away from the population mean right here. I'm not actually telling you what number that is, but let's just look at it as an example. With a smaller sample size, that tick mark right here is, or that distance from the population mean is still a likely outcome, meaning we're actually likely to overestimate the population mean by this much. But when you use a larger sample size, that same outcome now falls into the unlikely area. So this amount of overestimating right here that we were likely to do with a smaller sample size is now unlikely with a larger sample size, which is a good thing because we're likely to get a sample mean somewhere really close to the population mean. We're likely to get good accuracy in this narrow area, and we're unlikely to get anything outside of that. And I hope this video was helpful. I'll make one more video about estimating a population standard deviation with a sample standard deviation.